So to continue modeling with kinematics in one dimension, so let me put one-dimensional motion. We're going to study a special situation, but you have to know how it's special and when it's okay to use it. So let me put this. You must be careful. And I'm just going to put that. So the sense in which you must be careful is what I'm about to describe is only true if you know that you are thinking about a constant acceleration problem. So constant acceleration means that the acceleration as a function of time, which is the time derivative of the velocity, etc. This is what you know. You know that the time derivative is 0. So constant acceleration means that the acceleration does not vary in time. That's what it means. So you're only allowed to use what I'm about to describe if that's true. But I'm going to show you that that's implied. So let me show you. So there is a generic form of x of t, and it looks like the following. There is an x sub 0 initial position plus initial speed times time plus 1/2 the acceleration times the time squared, where this acceleration is, I don't have a little initial, and nor do I have acceleration as a function of time. This is just some constant value a times t squared. And the idea is since you are guaranteed something about the problem statement that you're reading about, something about the problem you want to solve has led you to believe that you are dealing with an acceleration that's not changing in time, then you can use this generic formula. So if I ask what is the position at time t equals 0, it's just equal to x sub 0 plus 0 times v naught plus 0 squared times a divided by 2. Another 0. So x of 0 is just the initial position. So v of t is just a time derivative away. So v of t is d by dt of x of t. And if you go take d by dt of x of t, here's x of t. It's these 1, 2, 3 terms. The first term has no time dependence. The second term is a constant times time to the first power. And the third term is 1/2 times a, which is a constant, times t raised to the second power. And when you take the time derivative of the first term is a 0. The time derivative of the second term is just v naught. The t goes away. And the time derivative of the third term is equal to, so it's 1/2 a, but then it's 2 times t to the first power, right? That's how you'll take the derivative of the t squared. The 2 comes down, and the t gets left over with a power of 1. So that 2 that came down, it combines with the 1/2 to turn into a 1. And so when you clean this up, it just looks like this, v naught plus a t, where a is the acceleration, and v naught, the meaning of v naught is just, it's associated with the value of the velocity at the time t equals to 0. This is the initial velocity, right? Then a of t is just d by dt of v of t, and v of t is right here. So let me be clear. So v of t is v naught plus at. d by dt of this business here is just, so the time derivative of a constant is 0, plus the time derivative of something that's linear in time is just the coefficient. It's the slope of this straight line function, and you just pop out a with no explicit time dependence. And so earlier I said that the only way that you're allowed to use this generic form for accelerated motion is if you are guaranteed you know that the acceleration of the object in question does not change in time. And here, what I've showed you is if you go and you look at this motion is constant in time acceleration. So yeah, to begin with, it was just a constant time acceleration form. So you got to learn how to use this form to solve problems. You can use this for free fall problems. And the idea is, instead of x of t, you might be doing y of t. Y tends to be like an up-down coordinate system axis. And then you can have the velocity in the y direction as a function of time is the time derivative of the position in the y direction as a function of time. And then the acceleration for free fall problems is just equal to the acceleration due to gravity wherever you're doing your free fall problem. It could be Earth acceleration due to gravity, or it could be Moon, or any exotic location like that. And you've got to be really careful choosing what sign to keep. Yes, so I'm going to make a video describing how to choose a sign. On Earth, what you have to make sure, for example, is that you're using 9.8 meters per second squared, but you must use it in the down direction. Yeah, because stuff falls down on the Earth. Okay, so before I do this example for you, or I might do 2 free fall examples, really quickly, let me go back a couple of pages and just show you where we started in the previous video, actually. Here is position as a function of time, constant in time. Here is position as a function of time, linear in time. Here is position as a function of time, so-called quadratic in time. Quadratic means that sometimes if you have problems that look like this and you want to solve for t, you have to use the quadratic formula. And functions of this type look like parabolas, for example. So I'll put the word parabola. Yeah, so this is quadratic, parabolic style functions. But what if, so these are all so-called polynomials. What if x of t is non-polynomial? So it's not written down as like a t squared plus a t cubed even, or a t to the 5th. So it's non-polynomial. So let me show you where that could go. So I'll continue for a few minutes, and then I'll make another video. You'll have to switch videos to look at how that continues. And then I'll do a free fall problem for you after that, or actually 2 free fall problems probably. So what if x of t is non-polynomial? So here's kind of a funny example. What if x of t is actually sinusoidal. I want to use a sine function, like a trigonometric function. And if it's sinusoidal, sinusoidal positions, like they kind of go like this. So imagine the pen is the object, and it's just going back and forth like this. This is sinusoidal in time, back and forth. Um, so I'm going to make a sine function where the argument is the time-dependent thing. So sines, what you put inside the argument has to be an angle. But the angle that I'm going to put inside the argument is going to be time-dependent. So let me show you how that goes. So this thing looks like a W, and then here's the time-dependent part. It's just W times T, except for this thing that looks like a W actually has a special name. It's omega. And omega is like a stylized W. It's a Greek letter, so Greek letter, lowercase omega. And omega is, in our problem, omega is going to be a constant. But because omega times t has to be an angle, I'm going to keep this angle in radians. So you're about to see some pi's. So if omega t equals an angle, that means that omega needs to be angle over time. So angle over time times time is an angle. So as an example, I'm going to choose the value for omega as 2 pi radians per second. So you can see that if omega is angle per time, then angle per time times time is going to give an angle. And sine functions, they only evaluate on angles. Okay, so, but whenever you take the sine of any angle, the sine of any angle has no dimensions. It's a sine function. It goes between +1 and -1, just back and forth. So I'm going to put something in front called an amplitude, but that amplitude needs to have the right dimensions such that the position has some meters in it, for example. So I'm going to give an amplitude of 2 meters, like this. All right, so 2 meters times sine of omega t, where omega is 2 pi radians per second. So maybe I'll make it more explicit. So 2 meters times the sine of 2 pi over the second radians times t, like this. But you know that this 2 pi radians per second is also known as omega.